Okay, thanks everybody for joining in. Andrew, interesting enough, I had a quick look back and realised it's probably been 10 years since I did my first presentation for WoodSolutions. Actually 12 years, 2010 was the first year I did a presentation for WoodSolutions. So nice to still be getting invited back. This presentation today is really a brief overview of some of the very large scale experiments that we've been carrying out over the last, realistically, it's probably been close to 36 months now. It's been over 3 years that we've been working on this, and to go through simply how these were set up and why, look at some of the results and look at some of the findings as well, and try and do all that in about 30 minutes. So aim is to go through this relatively quickly, but hopefully leave some time for questions. And also, obviously, there's the ability to contact me as well separately if you do want to ask questions separately. So the primary aim of the research that we are looking at, and the outcome of these fairly large experiments, has been driven by the desire to have taller mass timber office buildings, large compartments, large open spaces, open plan offices, and realistically doing this at a high rise level. And obviously different countries and different locations, high rise means different things, but realistically it's sort of 7 or 8, 9 stories, and having very different sort of requirements from a code point of view with regard to what is expected for the fire performance and the building performance as well. So the issues are that architects, owners, and obviously occupiers as well want to see the timber, and that we're seeing a lot more of that, and there is a growing trend to having a lot more timber being exposed. And part of that is the sustainability story, and wanting to obviously ensure that we have that sustainability story in some ways right out front, and that's part of the driver for having mass timber. But also, there's also another driver behind that, and that's the differentiator that these buildings make. So, but when we have exposed timber, if we have a fully developed fire that's not controlled by sprinkler protection, it introduces a significant amount of extra fuel because it's a combustible part of the structure, and we know that that has a significant impact on both the heat release and the decay of the fire. And it's in some ways that initial stage of that growth period, which is of real interest, and also that decay period, which is of real interest as well, especially how these how fires develop. We've got large areas of exposed timber in large compartments. Now, we know from compartments where we have non-combustible materials, steel or concrete, that when there is large compartments, we don't typically get flashover type behavior. So we don't typically have the whole compartment burning all at once. We have fires which move through the compartment. They've been termed traveling fires, and there's enough of evidence and information to be able to see how that occurs in larger compartments where we have specific sort of ventilation, and we get this different sort of fire compared to a smaller compartment where we get everything actually burning at once. And so we know that occurs for the non-combustible compartments. We know that when we have timber involved and it's exposed, and we have a fully developed fire, that the timber and the fire interact with each other, and the fact is that the fire impacts on the timber, but also that the timber impacts on the fire. And there's actually a circular process there, a feedback process that is very different to a non-combustible compartment where we've got steel or concrete. So there's that feedback between the exposed timber and the actual fire, which is of real significance, and part of the information, which is why we wanted to study these large experiments. And as I said earlier, when we're designing for high-rise buildings, we need to understand how the structure performs and understand how it performs through decay. So it's not just a matter of having a 60-minute rating or a 90-minute rating. It's also a matter of determining how the structure will behave when the fire decays, and how the structure will respond to that decaying fire as well. So what do we know? Well, we've actually, over the last sort of 7 or 8 years, there's actually been quite a large number of smaller scale experiments with exposed timber, and these have occurred globally, and sort of counting them up, there's been well over 40 of these where a certain amount of timber has been exposed, or potentially large areas of timber have been exposed, and we've had certain types of fire, whether that's gas burners, real furniture, or wood crib type materials. And so from all these experiments and all these sort of tests, we've actually learned a lot about how fire behaves when we've got exposed compartments, especially where these are relatively small. So up to 90 square meters is a relatively small compartment, and a lot of these have been based on residential type fires, residential type setups. So we've got some really good, useful information, and this information that has occurred and has helped change codes, it's helped change standards, and it's helped influence the way we design mass timber buildings. And it really has been a significantly fast learning curve in some ways to take some of this research and start to put it into action. What has come out of this is, of course, that the area of exposed timber actually matters. The type of timber you're using, whether you have glue line integrity or not, really does matter. The heat release rate and the decay is important. And the fact that if you don't have reliable encapsulation, so if you're protecting the timber and preventing it from the fire, that needs to work for the whole period of the fire, including the decay period. And where you're intending not to have the timber exposed, that encapsulation is actually really, really important. But what do we not know? Well, this list could be very long, and I think it should be, but just some small highlights as to what we don't know. And I think part of this is when we've got large compartments, there's a fundamental, structural engineering fire behavior which we assume for non-combustible compartments, and that's the impact of ventilation and this issue of traveling fires. And so if we're unsure how the impact of ventilation impacts fires on large compartments with exposed timber, then that's an issue for us, because there's a whole lot of underlying correlations. There's a whole lot of underlying sort of classic fire dynamics that we're relying on for that. And if we're actually having to understand that maybe there's a different fire spread mechanism, then that also is really important, because it starts to put a question the sort of underlying themes we have as to how we assume a fire will grow and sort of develop with the fuel that's burning with a certain amount of ventilation and then decay. And we've got a lot of work on that for non-combustible compartments. For larger compartments without timber, we have obviously a significantly less amount of information about this. There's some other really interesting parts which haven't been researched as well, or haven't been researched enough. How do we get and make sure we get a predictable decay? And that's really important, especially when we look at risk and risk reduction. And I think all of us are aware of that, because there has to be someone to ensure the building. We as engineers have to sign things off and put our names on drawings and make sure that everything gets built properly and everything has to be constructed properly. And there's a range of different professionals who are doing similar sort of things. And then approval bodies and people involved from a firefighting point of view have to be ensured that the approvals have been met. And also the fact is that the building has a certain expected performance during the maintenance and over its lifetime. So all these are really important, and as part of that we need to be able to understand how all those interact with the actual timber building itself. Just last week we were having a discussion around smouldering behaviour, and Guillermo Rain from Imperial College pointed out that there hasn't really been any fundamental research on the smouldering behavior of structural, large dimension structural timber for over 50 years. So, the question is why, and the question is really, we need to be starting to catch up pretty quickly on this to understand, what sort of risk this is and what sort of hazard it is, and of course, how to mitigate it, because obviously we want to be able to design these buildings safely. And of course, we want to be able to make sure that we're doing that in a way which reflects the way the buildings are being constructed as well. So this diagram, some of you may have seen this before. It's a very simple little chart which shows compartment floor area along the lower side, and then basically a ratio of the surface area of compartment to volume on the left side. And pretty much if you've got a smaller compartment, then you'll be up on the left-hand side. Just the pointer. You'll be up on the left-hand side here, and this is where a lot of our current fire experiments have occurred, or fire tests have occurred, where we've got exposed timber. And even the non-combustible compartments, these ones with the in the reddish color, again, not significantly large compartments. When you compare it as to what we're actually designing and building, we're building very large spaces. So, our knowledge of compartment fires is actually fairly limited, and that's a concern, and it should be a concern for both non-combustible fires and for fires where we have exposed timber. And so we need to be able to fill in those gaps and be conservative and reasonable with the way we actually engineer. Importantly, of course, is this aspect of where we have a flashover fire and then where we have a travelling fire. The larger compartment, we have more travelling fire type of behaviour. The smaller the compartment, we have flashover type behaviour. And this is really a nice, easy way to be able to compare the amount of information we've currently got and what it is that we're actually building to illustrate why there is a gap currently. So these large-scale compartments, this is a consortium that was joined up between Arup CERIB, who are a French-based testing agency just outside of Paris, and Imperial College of London. Primarily, we were looking at fire behaviour for exposed CLT. That was the headline, and that's what we wanted to stick to, and we stuck to that the whole way through this program of research, and it's still ongoing as well. Though we have a number of secondary aims, and we have a number of different people with an interest who are basically leading research as sort of subsets under this main primary goal. As I said, we've been working on this for 3 years, and we're still going. And really, it's all about how do large areas of CLT exposed influence the fire. And in some ways, we actually have a really good baseline for this, because these experiments which these have been based on are actually replicas of 2 very large scale compartment fires that were carried out with non-combustible ceilings, non-combustible underside of the actual floor. And so for us, it gives us a nice baseline to work with. We've got exactly the same compartment, same fuel, same ventilation conditions, and we can compare directly between non-combustible compartment and combustible ceiling type compartment. If you want to understand more about the X1 and the X2 tests, the papers are referenced below, and feel free, if it move on too quickly, I can always provide those to anyone else who is interested in reading about those. So as far as the setup details, just some images and some simple information. 352 square meters on the internal floor area, obviously slightly bigger. Masonry walls around the outside. We had a steel beam running along the middle, which was all protected, as you can see here, to allow us to not need to replace that, to save ourselves some money. And we had a CLT ceiling, which we put across the top. So it was spanning from side to side and supported mid-span. We also included 2 400 by 400 Glulam columns, and that was partly driven by a desire to understand how columns are responding to fire as well, and it's something which I have an absolute very much an interest in. And then we've got various different combinations of the protection and the type of fire protection as such within the space for the different experiments. A lot of instrumentation in this test and in these experiments, and we continue to change in some ways and improve on the instrumentation as we continue to work through these as well. None of this was loaded. No need to sort of load this at all. It wouldn't change the outcomes, because in the end we're looking at the aspects of the fire dynamics and wanting to understand in some ways how the timber itself performs with regard to the fire. And we're wanting to have relatively short fires because, as I said, we're interested in that early stage, and we're interested in that decay period. And we also wanted to make sure we understood exactly how the fire responded after it was naturally allowed to burn out. And so we collected data through all the instrumentation for over 3 days after the fire, which we thought was incredibly important to be able to do. So it was 4 experiments. The first one had all the windows and all the openings exposed, and it really is it's a sort of well ventilated compartment, but not incredibly well ventilated. The second one had 50% of the openings, and so it was very much an under-ventilated compartment, and in both situations all the timber was exposed. Experiment 3, we actually had a smaller area of fuel and actually installed a mist system within one corner, and that's an image of that actually occurring here. And the setup of the fuel and the setup for this is based on the FM 55660 standard, which provides a methodology to be able to test a mist system. And we basically installed an off-the-shelf mist system, got a contractor to come in, put that in, and carried out a test with that mist system fully operational to be able to see how that performed. And then experiment 4 was the same as experiment 1. We simply included 50% encapsulation down the middle, and you can see sort of some of the setup for experiment 4 just here. So as you can see, experiment 2, we changed one variable from experiment 1. Experiment 3, we changed one variable. We happened to be introducing a suppression system to experiment 1. And then the 4th one was again changing one variable and encapsulating 50%. So we've got the ability to be able to very carefully and very very into a level amount, a certain high amount of detail, compare the outcomes of each of the experiments. So just some visuals, setting up with the compartment, setting up the wood cribs. We used wood cribs but because they're repeatable, and partly driven by the fact that this was the same fuel that was provided within the X1 and the X2 tests. So from our point of view, having the same window dimensions, the same internal dimensions, and the same fuel was very important, so we can actually compare, as I said, non-combustible to combustible compartments. Mohammed standing next to some of the timber columns and in the process of putting together an enormous amount of instrumentation which occurred. That's the building just before the first test during the day. And these tests were actually carried out at night for a number of different reasons and partly driven around timing, but these were, and so some of these images you'll see very much a dark background. That's sort of because they were obviously with the sun had set and certainly made some dramatic photos. This is ignition for the first test, and this is how the first test started. We had a set number of pans which were ignited exactly at the same time across the fuel. The fuel was set back from one end and then was placed all the way to the far end of the compartment. So it's just some images from the first test, and I'll just quickly run through these. Obviously, the fire has just started to take hold. The pans have all been ignited, and we've got some flames starting to sort of get ourselves up to sort of 2 to 2.5 meters. Now, these images, next ones, are all from disposable sort of cameras sitting in the window, and you can see some of these other cameras sitting in here. A number of these cameras we thought we had protected them relatively well. It turns out we didn't. We learned from the first test that a lot of these cameras pretty much melted. We had to have a different approach for some of the second tests, but some really interesting images here. So first of all, you'll see that we've got pretty intense plume occurring. We've got flames obviously impacting the ceiling and fire starting to spread. And as you can see, we're actually getting flames starting to spread along the timber. And importantly, we're not getting any fire spread at the moment along the wood crib. There's obviously some burning of the wood crib, but we're starting to get flames spreading along the timber. A few seconds later, not significantly longer, sort of in the order of about 10 seconds, we've got some very intense flaming occurring. We're obviously getting some charring and some scorching around here, quite a circular pattern. We're obviously getting a lot of hot energy and hot gases hitting the timber and starting to move along. We've got a ceiling jet, very much a flame ceiling jet, moving well along the compartment. And as you can still see, we've actually still got the timber not ignited. So we're getting fire spread along the ceiling before we're getting fire spread along the timber. So quite an interesting mechanism of actual fire spread, and it's useful for us to be able to understand the details of that as early on as possible. And as you can see from this one, very much an intense fire starting to grow at the ceiling, starting to get this flame spread. And of course, in this situation, no sprinklers, no detection. It's all about trying to get ourselves the worst possible fire and trying to make sure that we're understanding the dynamics of this. And of course, the timber still hasn't, the wood crib still hasn't ignited at this point. And then we get to the point where we get enough radiant feedback that we actually start to get the wood crib igniting, and we start to get flames starting to then move very quickly along the compartment. Soon after that, we actually start to get a point where we've got the whole compartment realistically involved in a fire. Can't say we've called this flashover, but it was certainly, if there was a description of flashover, it probably looks very much like this. So this is a large space where we would expect there to be a travelling fire. In the non-combustible, the X1 and the X2 compartments, there was very visible travelling fire behaviour, where you had fire moving in a way which was evident that there was sort of a localised flashover sort of occurring and decay behind in areas where fire had yet to occur. In this situation, one absolute fire where everything is involved. As that started to continue to consume the fuel, we started to get a dying down of the flames. This is at this closest end here is where the fire started, and then a lot of flame extension further down. And so we're starting to get the flames actually starting to recess in the fire, and the fuel starting to be consumed, and it's starting from the ignition end, starting to move down the compartment. Just an image of the timber columns, which are well involved in the fuel at that point. And then around 20 or so minutes later, as I said, we've got a really quite a rapid growth stage. We had a relatively short fully developed phase because we had a relatively sort of small fuel load, and that was fine because what we were then after was understanding how that decay occurred. Whether that fully decay period occurs for sort of 5 minutes or 50 minutes is in some ways not as relevant as that initial growth phase and that decay period from our point of view. And so we're starting to see here where the flames have certainly ceased on the CLT. We've got very little, if any, flaming on the actual fuel itself. We've got one of the Glulam columns here. just sort of glowing away. This is a protected steel column, which we put in all of these. We had a protected steel column, which in some ways is all about benchmarking, and there's some more information about that on the published papers as to why we included the steel column as well. And so let's have a look at some of the results, and I'll just quickly flick through some of these. So this is the actual heat release rate, and these sort of shaded areas are basically the areas of error with regard to sort of how we can measure estimates of heat release. And as you can see, we've got quite a rapid growth phase during the period, a reasonable period of burning, and then a decay where very quickly the fire actually dropped down from a heat release point of view from a peak down to sort of quite a low decay period, and then a very slow sort of decay in the heat release in that sort of 10 to 20 minute period. So as you can see, the heat release is made up of the columns, the CLT, and the actual wood crib itself, of which the majority of this is actually obviously the wood crib and the CLT. And combined we get that total heat release. From a temperature point of view, just explaining here, these are four graphs of temperature, and these are located at these points, T1, T12, T14, and 16, which is just the thermocouple trees, so along the compartment, ignition at this point, and then moving along through the compartment as such. And this is pretty much down the strip, down the centre line. And what we've got here is a comparison of experiment number 2 and experiment number 1. So experiment number 1 is actually in this red area in these three parts here. For this location, we didn't have a thermocouple tree. In this location, we started to add extra ones in as we moved along. But you can see the difference whereby the fire in the second experiment was certainly longer with regard to the temperatures, and we get a slower decay, and that's the impact of that ventilation, having ventilation which was half of the first experiment. And so you can see those differences in the temperatures, but also you can see a fair amount of uniformity between the beginning and through the compartment. When you look at the type of compartment, the type of temperatures we're recording, there's actually generally a fair amount of pretty much good uniformity. What is evident as well is the fact that there is a very slow decay in the compartment as well. If we compare the actual drop off in the heat release rate, we have quite a rapid drop off in the heat release of sort of that 15 to 20 minute mark, which is sort of up into here. But the temperatures are actually very slowly declining. And I think there is an important aspect here which we've seen in the smaller compartments, and we certainly see it in this compartment as well, where there is somewhat of a disconnect on the decay side between the temperatures and the heat release rate. As far as temperatures go, these are temperature slices just through the centre line, and just some imagery of what was occurring at the same time. And as you can see, this is between sort of 5 minutes and 6 minutes and 20 seconds, so it's a pretty short period. But as you can see, we sort of had this temperature of relatively hot gases moving along the compartment, and we saw that earlier in the images before, which continued to burn, and then we started to get fire spread where we were getting flaming across the CLT and flaming of the actual fuel as well. And then we get to the point where the whole compartment is actually combusting. We've got the situation where we've got a large amount of flame extension, we've got a lot of fuel that's burning outside the compartment. There is just not enough oxygen that's in the compartment to be able to burn everything, so we get a lot more flame extension, even in a compartment which has quite a high amount of ventilation, such as this first experiment. Also interesting enough is the fact that there is not a great deal of sort of two-zone sort of temperature difference here. We've very much got temperatures in most of the locations sort of in the 650, 700, 800 degree zone, and we're getting those right at the floor all the way through here. So we certainly have a situation where we've still got difference in temperatures, but we do have a lot more sort of uniformity of the temperatures. And we also have confirmed some other research which has shown that the peak temperatures are often not quite at the ceiling, they're actually slightly below the ceiling. So that was useful for us to be able to confirm some of the smaller scale research which has shown those similar sort of behaviours. As far as the fire and this aspect of travelling behaviour, what this graph is showing here is we've got time and we've got distance from the ignition, so distance from one end moving along the compartment, and this is tracking the CLT and where the flames are on the CLT. And as you can see, these are always ahead of the fuel. So there is a gap here where the flames occur on the CLT before they do on the fuel, which is somewhat reverse to what we see in a non-combustible compartment. So from a travelling fire behaviour point of view, yes, there is a travelling fire, but is it the same as what we would normally expect? The answer is no. Are our current correlations therefore valid and relevant? That's a very good question, and we're going to be spending quite a bit of time working on that, and Imperial College will be spending quite a lot of time looking at that and digging into that to find out exactly why there is this difference, and the difference that's relevant to having exposed timber. So, this is sort of the crux of the issue, is this aspect of having the leading edge at the ceiling rather than at the fuel, and that's a pretty important finding from the experiment so far. As far as char depths go, you can see here that experiment number 2 had a slightly higher char depths than experiment number 1, though not significantly different. And again, less ventilation for experiment number 2 meant we had a longer duration fire, and you saw that in some of the temperature graphs earlier. And so we would expect there to be a slightly deeper amount of charring, but again, not a significant difference, but a difference that we would expect given the fact that we've got differences in ventilation and different fire that would therefore come out of this. So just to start to wrap this up, some of the significant findings. So first of all, I'm not going to read all through these. I wanted to put them out there so people can read them themselves and potentially take these away, because I think it is useful to have some of these early findings and have some of this information out there. We do, as I said, we do get a fire to travel, though the current methods we have certainly do need to be adapted and amended as to how we predict that travelling fire. Certainly it's something we cannot do at the moment. The existing correlations, existing inputs are different, and we need to be able to work on how to amend those to be able to ensure that we are getting the right predictive models. The external flaming was certainly significant, and our existing correlations for those certainly are probably not as accurate as they should be. There's more research going into this in various different locations. Certainly RISE in Sweden are doing some really good work on looking at external flaming in compartments, and it'll be useful to see what their outcomes are, and sort of there is some overlap in the work that they're doing, the work we're doing, and certainly we've got a small team looking at that and trying to work out how to best look at those correlations and how to improve on those. Our existing compartment models really aren't doing what they should. We don't really have a compartment model that was even close to accurately predicting the fire, the time temperature that we got out of these experiments. And it's always useful to be able to have some more data points to be able to look at how to change those. Certainly Daniel Brendan's work has been excellent in this area, looking at the compartment models. And I think, as far as the most advanced model, his is certainly well out there, and there's certainly been others which we've started to look at as well, and working out, trying to find ways to be able to work and looking at how we can amend some of those current models and what are the factors are that need to change. And a lot of those are related to the decay phase and how we account for the decay phase. Smouldering has been significant, and there's a whole separate work on smouldering in here, and I haven't really had time to touch on that. And that we did see some really interesting areas of smouldering in some of the interfaces. And it's important to understand that smouldering will occur where we've got timber to timber interfaces. We see it in standard fire tests. We see it in all the experiments that have been carried out. It's very easy to be able to suppress the smouldering that we had was stopped by a rain shower, but it's all about how to detect it. How do we make sure that we find the smouldering? How do we detect that? And then how do firefighters respond to that? Do they have the right tools? Obviously, different firefighters in different locations. Some already have the right tools and have the right equipment. Others may not. And that's part of the process, I think, that we want to make sure that occurs for mass timber buildings, especially high-rise buildings, that there's awareness of what the smouldering risk is, and then how to actually mitigate that and ensure that we get some, the right tools in place to be able to ensure that that does occur. The thermal penetration and timber degradation that occurs certainly in columns is something that I'm spending quite a bit of time looking at, and I think it's an important part of the way we design tall timber buildings. There is certainly a lot more work to be done on this. It's something that I've been looking at for quite a number of years now, and there is a good some really good data sets looking at how temperatures move within within timber, and certainly what occurs post-peak fire. So actually, often we see that the peak temperatures in the timber actually occur well after the fire has peaked and started to decay. So your temperature curve in the compartment may be going down, but your temperature in the actual timber may still be rising, and that certainly is important where we have timber elements which are quite vulnerable, like columns. And so, again, we'll be spending more time in looking at publishing on this. And ventilation, significant. Started off with ventilation, going to finish in some ways with ventilation as well. And it's incredibly important to understand how the ventilation does impact fires. And this is, most of you, hopefully from a fire engineering point of view, would recognise this diagram, and what's plotted on here is a range of other smaller scale mass timber experiments, and you can see that nearly all of these are above the curve, and it's been interesting. There's been quite an amount of research looking into this. There's some really good published papers on this, and it's worthwhile, if you are interested, to understand how ventilation and fire dynamics are changing with mass timber, to read on this. And when you look at the two experiments from our point of view, which are included on here, you would say that they're pretty much working like a classical sort of larger compartment. And the fact that we've got a fuel-controlled fire sitting, well within the curve, we've got a ventilation-controlled fire, which is sitting here not too far from the curve either. But the reality is, this doesn't tell the whole picture, simply because when you see the imagery and see the fact that the fire behaved very much as an under-ventilated fire in both situations with quite large flame extension, there is obviously a difference that is occurring between the fire dynamics, which are predicted by something as simple as this simple opening factor versus temperature curve, which has served us very well for well over sort of 50 years, and what's actually occurring with these larger spaces of mass timber. So there is some important aspects here we need to work through just from the basis of some pretty basic classical fire dynamics, and that's part of the work which we continue to work on with Imperial and CERIB as well. So what's next, just to finish off, we're about to publish a fourth paper on this. There has been 3 which have already been published. The experiment 2 is just about out. It's certainly been accepted. We're expecting it to go online sometime, hopefully in the next 2 to 3 weeks, and all of them are just below there on the screen. It's currently supporting 3 PhDs at Imperial, and probably potentially other postgraduate work will continue as well. There is, we've got to look, our aim here is to make sure we've got good engineering methods for large open plan offices, and we want to be able to make sure that we're getting those good engineering methods out there and completed. And there is still a lot of work to do. After the burns, there is an enormous amount of data we've got to sift through, and an enormous amount of sort of work that needs to occur. And certainly that is something which we continue to do, and we'll continue to do through this year as we look to sort of publish on as many papers as we can on this, to be able to get this information out there and start to have others also look at the findings as well. So lots of people to thank who were all part of this team. It was a great team, and we continue to collaborate on this. We continue to work on all the information and getting the theory out there and getting the results as well. There's more information on the Arup page, which you can go to, and obviously you can contact me directly if need be as well. So thank you very much, and I'll now hand it back over to Andrew.
Thank you, David. An excellent presentation. It's a great deal of work there and great deal of knowledge, and I recommend anybody wants to know more, follow up on David. And it's a perfect segue to our next speaker. But firstly, anybody has any questions, please type them into the Q&A, and we'll address them at the end of the next presentation. So the segue, Dave's talked about what the issues are, and Paul's now going to talk about what the Australian version of this open plan testing. So welcome, Paul, to conduct your presentation.
Okay, and I just like to say a big thank you to David and Arup for sharing their research. It's nice to see a large consultancy getting involved in some research and promulgating it for the whole industry. So, and as David said, it does lead in very nicely to this presentation, which is looking at the proposed Australian mass timber full-scale test program, which is looking at, funnily enough, large open plan enclosures. So the primary objective is to demonstrate the fire dynamics associated with major fires in large open plan enclosures, pretty much the same sort of sphere that the Arup tests were looking at. But specifically, this is going to be looking at exposed mass timber elements, beams, ceiling, columns. It's also going to have a good look at glazed curtain walls. David's presentation and the work undertaking clearly demonstrated that ventilation plays a significant role, and most of the test work that's been carried out so far assumes a certain ventilation configuration and assumes that all the glass is missing. With glazed curtain walls, it's possible that the ventilation will be modified by, well, it will be modified by the curtain walls until they break. And the time of breakage, when you're talking about pretty thick, toughened glass, will vary a little bit. So that's going to be a major feature of the full demonstration test at the end. Also, looking at representative fire loads, it's very useful to use things like timber cribs, and they'll be part of the preliminary series of tests in this program. But timber cribs, pool fires, etc., they tend to burn very uniformly, which is good in a way, but they also decay quite rapidly at the end. Liquid fuels very, very quickly, and timber cribs, if the sticks are all the same size, also decay quickly. So what happens is the decay phase is potentially unrealistic. So we'll be looking at trying to do the demonstration test with a representative office type furnishings, etc. There'll be no sprinkler protection, even though the buildings have sprinkler protection in, and we shouldn't forget that. But obviously we're looking at the fire dynamics if the sprinkler system doesn't operate. Fire brigade intervention is going to be looked at occurring after the fire has decayed to address any minor residual smouldering or flaming combustion. This is an outcome and was seen in the Arup tests, and David was explaining. So we'll be looking at delayed fire brigade intervention, and again, we'll provide some useful information with a real fire load or a simulation of it, and again, a large enclosure fire. So the program is intended to fill knowledge gaps and provide an increase in confidence in the application of performance-based design methods, and also for the further development of deemed to satisfy solutions. So that's a big overview. Just a little bit more detail. There are 4 general activities. The first one is modelling. So we'll be inviting some of the sponsoring practitioners to undertake modelling before and after each of the stages of the test, which really will reflect the state of the art. It's a bit brave to do that, and again, we appreciate the efforts that they'll be making. So after each test, they'll be able to look at their results and then see how they can be improved. And hopefully we'll get a good spread of analysis methods from hand calculations, potentially through to CFD, and get some understanding of how effective those models are and what the state of the art is. The activity 2 is then looking at some experimental programs, and again, the modeling will run into all these different activities, but the preliminary experiments will be looking at scaling. So we are going to do some scaling tests, even though we finish with a large scale experiment. The reason for that is to gain an understanding of some of the variables before we carry out the full scale test, but it's also to see how reliable scaling can be for these type of configurations. Unfortunately, it's not possible to scale all parameters in a fire scenario, so there's always a compromise, and the scaling of certain parameters isn't that good. So it's got to be optimized. So as part of the initial program, we'll be doing some work to look at optimizing the crib design and to match the enclosures. And I'll go into that in a later slide in a bit more detail. Then we'll be undertaking a full-scale demonstration test, which will be nominally 20 meters by 20 meters, so that's 400 square meters, and with a 3.5 clear height to the ceiling, but there will be beams penetrating below that height. And finally, activity 4 will be reporting and dissemination. Formal detailed reports will be provided to the participants to give them some advantage for their contributions, etc. And with a restricted release. But that doesn't mean that the results are not going to be published at all, or that they'll be substantially withheld. So there will be some results which will also be reported in appropriate technical journals and by FWPA publications, etc., prior to the general public release of the detailed reports. And after an agreed period, the results will be made fully available. Well, that's the intention. Obviously, this is going to be run through in a little bit more detail. So looking at the modelling, as I've said, it'll be done prior to experiments, updated as the experiments are done, prior to the full-scale test, and again updated after the demonstration test. So it gives an opportunity to develop some analysis tools. Looking at the scale testing, again, this is not fully fixed yet, but there'll be a small, medium, and full-scale testing, probably done at quarter, half, and full, or third, 2/3 full. Again, this is going to be selected to try and match existing data that we can also tie into as well. So if we go with a 2/3 scale, we might end up matching the ISO room burn, which gives a lot of information on fire initiation and development. The intended configurations include free burn tests on cribs to quantify free burn pyrolysis rates. So this is looking at that growth phase, which is very important. So we want to realistically represent that. Scaled timber cribs will be below the ceiling with perimeter beams to investigate the scaling of that growth phase. And we'll also do some enclosures with the fully developed enclosures to make sure that the timber cribs and design of openings and wall enclosures are scaling reasonably well. So once we've got that satisfied, that we will do some scale tests representing the larger scale test that we're going to do, and they're shown on the left of this slide. The different ventilation conditions can be seen that we're running through, and this is to really be looking at what level of ventilation you're going to get if some of the glass breaks, if all the glass breaks, or as it varies through. So the top left, you can see a little red line. That's a relatively small opening, and we'll see what the spread will be like there. The fire will be started close to these openings, so it's simulating a scenario where the glass is in close proximity to a window and therefore breaks a window, and then you get that ventilation. So there'll be a number of different scenarios, and we'll look at it. There was some work done very early by VU on long, thin enclosures, and they started fires at the front, which instead of progressing all the way along in one hit, they actually moved to the back of the compartment and then back to the front of the compartment, so you can get uneven heating there. So we'll be looking at those sort of things, again, subject to getting sufficient interest and contributions. We'll also be looking at different ceiling profiles, so flat ceiling versus a ceiling that's broken up by beams. Then looking at the full-scale test in activity 3, we'll be looking at a glass facade. So that's, as I said, is examining changes to ventilation condition as the facade glazing falls away. Another feature will be that we'll have a small office enclosure above with the same glazing detail to examine the risk of fire spread, because again, it's not just the breakage of the glazing in the enclosure of fire origin, it's also potential breakage or the resistance to that from an external plume. So that will be examined in some detail. We'll also have a protected shaft evaluation, which gives an idea of the safety for firefighters to approach and fight the fire, and also for the other floors in the building to evacuate. As we said before, there'll be a representative fire load and a representative ignition source. This early growth is very important to look at the potential for evacuation, and we'll also be including a detection system, an exit signage in to have a look at what time an alarm's raised, and also to look at what the visibility will be like in a relatively subjective manner to get a time available for evacuation. Horizontal section, rather boring view, but essentially you can see it's the large scale test will be done with primary and secondary beams, and that will obviously have impact on the fire spread. So there are quite a few opportunities for participants to supply systems for demonstration purposes, slab edge details, facade details, service penetrations, cavity barriers, timber beam connections and other joints can be looked at. That also gets into issues with smouldering, etc. Access floor performance, detection alarm system, emergency lighting, curtain walling, and inclusion of services and associated fixings below the ceiling as well. So what's next? We're looking at confirming participants hopefully before the end of the financial year, modelling and scaling experiments to 22-23 and the full scale test in 23-24. And if there's any questions, you can ask myself or Andrew, and Andrew will probably give you a bit more detail at the end. So thank you for the opportunity just to give you a quick run through of what the programme's about.
Thank you, Paul. Excellent. It's a good segue for all of that. And now we're into the question and answer section. We only got 2 so far, so please, if you've got any questions, please type them in, and we'll have them answered. So we've got a few minutes till the end of the webinar. So firstly, there's an anonymous one, and to you, David. There appears to be a lot of study around fire. However, some reports from fire authorities suggest smoke presents as a significant issue and often not represented or spoken to well. What are your thoughts around this?
Yeah, well, I think part of that is the fact that it's the smoke that is toxic and is causing issues for people when fires occur is not related to the structure. It's related to the actual materials. You know, the bedding, all the plastics, it's all the other the materials that really are not part of the structure, and they're the ones which are causing a lot of the issues. In some ways, you know, it's large screen TVs and the plastics and everything associated with those that are you know, incredibly toxic. So, but separate to that, I think there has not been many studies looking at how timber burns and the toxicity of it, simply because the work that has been done has shown that it has never really been an impact. There is so many other items of combustibility within a normal space, whether that's office space or a residential space, that are so much more toxic because of their materiality that timber is such a small amount of the actual, in some ways, you know, the larger issue. So it is, I think, more of an issue of the fact that the timber is not contributing more to the smoke, and it's certainly not contributing the toxic materials that are life-threatening that you get from the contents. And I think that's, you know, the important thing to factor in here. So it hasn't really been looked at, but we know that on a smaller scale, the timber really is not causing the issues compared to the contents. I think that's probably the best way to answer that.
Thank you. Okay, next question. Mario, does the charring depth correlate with the formulas in 1720 Part 4, the timber charring standard? Did you have a go, Paul, on that one?
Well, I haven't actually done a detailed analysis of the Arup experiment, but the charring rates vary with the exposure. and therefore it really depends on the exposure. So if you vary your heating regime and your oxygen content from a fire resistance test, you will get a different char rate. Interestingly, the char rate or the oxygen content in a fire resistant furnace is usually around about 5 to 10%. It may drop below if you're testing timber, it may not, depending on where you measure it. But the oxygen content tends to be very low, close to timber elements during natural fires as well. Therefore, the oxygen content is certainly realistic of a ventilation fire. With a fuel control fire, could be a little bit different, but your heating rate and your exposure will potentially cause acceleration of the char rate. Whether those average out over the length of a test depends, but you'll normally get some variation from 1720 part 4 char rates.
The answer is no there, Paul.
Yes, in a long way.
Exactly. The answer is no.
Thanks for that, Paul. A question from Doug. Have fire retardants boron been considered in Glulam to increase fire resistance level? David?
I suppose in some ways there's a couple of parts to that. One, the putting fire retardants in is normally pressure treatment, and generally you have to pressure treat the timber before you then decide to turn it into Glulam or decide to turn it into CLT. You can't reverse that process. And generally the process for actually putting in fire retardants is actually kind of on a small scale. It's putting in 2x4s, 2x6s, 2x8s, those sort of things. So you don't have the ability to put large members into like long members into this facilities to actually get fire retardant treatments that would actually provide that sort of level of fire retardancy. The second part is that the fire retardancy that's generally occurring is more about the flammability of the timber. It's not really impacting the fire resistance. So the ability for the timber to support flames and support flame spread as such in that very early stage of fire absolutely can be impacted by fire retardant type treatments, whether that's potentially a paint on the outside or actually a pressure type treatment. But when it comes to fire resistance, they generally don't impact the fire resistance to any great degree. There has been some testing of that on smaller members, and it's shown that they have a pretty minor impact, but not of anything significant. So I think the answer to that is probably no. And there is a third part to that, is in the fact is we're trying to keep timber as sustainable as possible and try not to put any nasty chemicals in it. So I'd always be pretty resistant to doing that when we've actually got a sustainable material and trying to find other ways to be able to improve it from a fire point of view without having to do something which reduces its ability to be a sustainable material.
Okay, thank you, David. So just to add a little bit on that, one of the things that we may look at in the experiment that we're planning in Australia, but depending on sponsorship and on the amount of dollars available. But moving on, and we just really got enough time for one more question. And I'm just going to, Peter, one from Peter. Hello, is there any information available on post-fire damage remediation work required to ensure ongoing integrity safety of the building structure? Quick answer on that, David?
Yeah, I'm happy to answer some of that. I think the answer is yes, there is. It's limited, and primarily part of the issue is that when you have a major fire which is impacting the structure, then the building is only one part of the equation of the actual damage. Contents is obviously a significant part of that, and loss of actual operational use is a big part of that as well. So for larger fires, it becomes more of an insurance question than a repairability question. It's up to insurers to determine whether a building can be repaired or because of the fire damage, smoke damage, water damage, etc. It is not worth repairing. So for smaller fires where there is enough damage for it to be structural, but there's the ability to still look at repairs. Timber is a lot easier to diagnose than steel or concrete. For the ability to if you understand what the member size was, and hopefully you do from drawings, the ability to be able to work out how far in the char is actually, quite easy to be able to do with a small drill, and to be able to work out the depths of those, to be able to work out where you've actually got into sort of ambient temperature timber. It's a lot harder with concrete and steel to take samples and get them tested and determine whether you've still got the strength or not. So that's one part which is useful. And then it's just a question of, can you repair it, and what cross-section do you have left? If you've got enough cross-section that you've still got enough structural stability there, then there is the ability obviously to add on additional timber and sort of provide that additional timber which was sacrificial as such, and so bring the cross-section back up to its size and still keep the retaining cross-section. If it's to go to the point where it is potentially structurally damaged and you don't have that ability to be able to just in some ways bring the cross-section back up to where it was, then it again becomes an issue of the cost in actually repairing, the ability to actually take out a column in a building or take out a beam and repair it is quite a significant undertaking. And again, that's a matter for insurers to make. But at least from an engineering point of view, the diagnosis from a timber point of view, we can actually do that relatively well and understand, where it is from a structural point of view. It's then just a question of costs and economics as to how much you repair, or whether it's too expensive to repair.
Thanks, David. I'm glad I didn't answer a long answer to that question. But on that point in time, we're now at 12 o'clock, so I'm going to have to draw this to a close. I'm going to thank my speakers, David Barber and Paul Lingham, for a brilliant presentation, and remind you this will be available soon on WoodSolutions website. So remember, the speakers will be sent to you shortly, and CPD questions are as follows. And just a reminder of future events are coming up. We have a WoodSolutions seminar in Sydney on the 18th of May. It's going to be at the Eric Tweedow Stadium, so a real mass timber building in Sydney. And more information for the Sydney people, go to WoodSolutions events page and register. The next WoodSolutions webinar is on the 10th of May, and it's another exciting presentation on the 694 webinar series. And we've got Afzal's going to talk about bracing design, specification and detailing. So for timber framing enthusiasts, look forward to that one. And just a reminder that the Australian Timber Design Awards are now open, and if you've got a project, please consider entering. And closing off, if you want to know more about the full-scale test program that we plan to do in Australia, that's my details below. Please feel free to email or phone me, and we're happy to discuss further. So at this point in time, I'd like to thank everybody for attending this webinar, and particularly the speakers, David and Paul. And we'll wrap it up now and say thank you, and see you at the next webinar.